So I wanted to actually evaluate the area, and we're going to look at example 1 to find the true area. So when you look at this object over here, the function that we're working with, the f of x is equal to x squared, and your AB is equal to 1, 2. And I can tell that just by reading the problem. All right. So, so let's do this example. So let me make this smaller here. Okay, so the first, yes, Terry, you're right. I just went to start this and I'm like, wait a minute. 1, 2, that was the last problem. 0, 1 is this problem. Thank you. For sure, AB is 0, 1. I'm losing it. So the first thing we want to do is we want to take our interval going from 0 to 1 and chop it up into n equal pieces. In this case, I don't have a specific number for n because I'm not doing an approximation. I'm going to calculate the actual area. So when I go to write down what my delta x is going to be, it's going to be b minus a over n. In this case, it's going to be 1 minus 0 over n, which is just 1 over n. Okay. And I'm going to need to figure out my f of xi star, because this is going to be the height of the ith rectangle. I know that this guy is the width. Okay. So in order to answer this f of xi star, I really need xi star. So I need a formula for xi star. Did we discuss this on the previous video? I feel like we must have, right? Hold on, let me take a look. Did we do the xi star stuff? Oh, we didn't. I could have swore I described it somewhere. No. Okay. So let me help you find the xi star. So when we work with the xi star, it makes a difference if you're doing the left endpoint or the right endpoint, right? So if we're doing the left endpoint, then we know that xi star is just going to be xi minus 1. So this is the general interval. The left endpoint would be xi minus 1. And how am I going to calculate what that is? I'm going to show you in a second. Okay. If we want the right endpoint, the right endpoint is going to be xi star. That's just going to be xi. So let's figure out what this one is first. Okay. So what we're going to do is we're going to start at the left edge of the interval I care about. And in our case, that's going to be A. And if I wanted the next x1, if I wanted that, to know what's the value of that, I just need to add 1 delta x. So this x1 would be A plus delta x. If I wanted x2, I need to add 2 delta x's. So this point right here would be A plus 2 delta x. And then what I do is I keep adding a delta x. So if this is the ith rectangle, I'm going to add 1, 2, blah, blah, blah. I'm going to add I delta x's. So this should be A plus I times delta x. And that's how we get the right endpoint. Is there any questions about this so far? So just to be perfectly clear, for x0, I'm adding 0 delta x's. For x1, I'm adding 1 delta x. For x2, I'm adding 2 delta x's. For xi, I add I delta x's. If you follow that, then maybe you could tell me what the formula for xi minus 1 should be. It's going to be A plus some number of delta x's that I add. Do you guys know what should go inside here? What do you think goes inside here? Any thoughts? Terry, you got it. Terry said I minus 1. Because if you're looking at the left endpoint, you don't go the full, you go 1 less, right? Going 1 less would take you to the left endpoint. So this is going to be I minus 1. So these are sort of general formulas for how you write down the endpoints. Okay. So for us, this is going to be 0 plus, let's do right endpoint. So this will be 0 plus I times 1 over n. We use right endpoint. I think using the right endpoint is easier, so I kind of always use the right endpoint. Okay. And this means that my xi star is just equal to I over n. Is there any questions so far? All right. So I'm in a position to solve this problem now. You're going to love it. It's going to be awesome. So the first thing we're going to do is we're going to write down what we're trying to calculate. So we want the area from 0 to 1 of x squared dx. And we know that's going to be the limit as n goes to infinity. We're going to write our formula for the Riemann sum, which is the sum as I goes from 1 to n, f of xi star times delta x. So this is just going to be, you know what, let me move it. This is going to be the limit as n goes to infinity. Sum as I goes from 1 to n. Your f in this case is the squaring function. So what I'm going to do is I'm going to take my xi star and I'm going to square it. So this becomes I over n squared. And my delta x was 1 over n. Is there any questions so far? You should ask if you have any questions. maybe I'll write a little bit more detail because I have room up here. So f of xi star is equal to xi star squared, which is equal to I over n squared. No questions. All right, perfect. So let's write the next line. That's equal to I times I is I squared. I mean, n times n is n squared times n is n cubed. So we get I squared over n cubed. Okay. Now, here I want to introduce something a little bit subtle to you. When I look at this expression over here, I sort of see two layers. The first layer is this part right here. And for this part right here, the variable is I, and really n is treated as a constant. N doesn't really become a variable until we take the limit. So for that first layer, n is treated as a constant. Now, I had showed you last section that we have all these rules. Where'd they go? The rules here. We have all these rules for manipulating our series. And our goal is to get one of these three sums. So the rule I want to use, I want to factor out a constant. Okay. So if we go back to this example, n cubed is treated as a constant because the variable is I for this sum. So I can really write this as follows. I can factor out the n cubed, and I just have an I squared like this. Does that make sense? Are there any questions about that? Well, if we get to this step, we're extremely happy because I have a formula for what that is. So that's going to be the limit as n goes to infinity of 1 over n cubed. And then this guy is going to be n times n plus 1 times 2n plus 1, all divided by 6. Okay. So we just need to simplify what this is. So I guess the first thing I'm going to notice is that we have an n on the numerator. We have 3 n's on the denominator, so I can really make that an n squared like this. And then I can multiply out the top. So this is going to become the limit as n goes to infinity. The top is going to become 2n. Sorry, hold on. I got 1 over n squared. That's still there. I'm going to multiply out the top. The first is going to be 2n squared. The outside is going to be n. The inside is going to be 2n. So that's going to be a 3n in the end. And then 1 times 1, the last is going to be 1. This is all over 6. So somehow I ran out of room. Guess I'll just move everything over. Like this. So what I'm going to do is I'm going to pull out the 1/6 because that's just a constant. So this will be 1/6, the limit as n goes to infinity. You're going to have a 2n squared over n squared plus I'm just debating whether I want to write an extra step. Right, so I have the 1/6 out in front because we're multiplying by a constant. So you can always factor a constant out of the limit. And then this means you just have an n squared in the denominator. So when you have an n squared in the denominator, I can split this into the sum of three things. So this is like 2n squared over n squared. This is like 3n over 3n squared. And then this is like 1 over n squared. Does that make sense to everybody? Are there any questions? Okay, so let's move it up here. So this becomes 1/6, the limit as n goes to infinity. You're gonna have the n squared and the n squared cancel each other out. So you're gonna just have 2. You're gonna have 1 over n. You're gonna have 1 over n squared. So at this point, we need to look at this piece, these two pieces right here. So if you were to calculate the limit as n goes to infinity of 1 over n, what do you think that limit's going to be equal to? Oh, sorry, there's no 3 there. There's a 3 here. My bad. This doesn't really matter what the top is. We put a 3 there. What do you guys think this limit is going to be equal to? Any thoughts? Can we all see that this limit's going to be equal to 0? Because it's like you have the top is a fixed number, but the bottom is getting bigger and bigger and bigger, right? So when the bottom explodes and the top is a fixed number, that whole thing is going to go to 0. It doesn't matter how big this top number is because the bottom is going to infinity. So any number over infinity is going to give you a 0. So really, this piece goes to 0. This piece also goes to 0 because the bottom is getting huge. So in the end, we're just left with 2/6, which is equal to 1/3. So your answer is going to be 1/3 units squared. And that's going to be your final answer. Does that make sense for everybody? Does anyone have any questions for me about this? So let me walk you through this whole process again, because I'm going to ask you to do this on a quiz later next week. Oh, wait, is that right? Is it next week? Or do we have our test next week? Anyways, I'm asking a quiz later. So how did this work? What happened was I realized from this notation, I want to find the area under x squared from 0 to 1. I identify all the pieces. I calculate the width of my rectangle. And then I calculate the height of my rectangle. How did I calculate the height? I chose to use the right endpoint. And I calculated the right endpoint using this formula. And my formula for the right endpoint is just I over n. When I evaluate my sample point at my function x squared, I get I over n squared. And then I just take my limit definition of a definite integral. I plug in each of the pieces. From here to the second to last step, it's all algebra. So we're taking this guy, we simplify it, we factor out the 1 over n cubed, and then I use my summation formula for I squared, which is right here. Okay. Then I simplified this limit. I factored out a 1/6. And when I simplified that fraction, I saw that the first piece is a constant and the second two pieces go to 0 because you have an n in the denominator and the denominator is exploding. So finally, I get an answer of 1/3 units squared. All right.